Greetings, Earth enthusiasts. If you ever wondered about the incredible perspectives our planet has to offer from high above, you're in the right place. I am Dr. Clive Coetzee, and I'm thrilled to be your guide on this captivating journey into the world of remote sensing. Welcome. And please remember to like, subscribe to, and share this video. Thank you.
Okay, so the last week or 2 weeks, we just played around a little bit with, with AI generated videos. I made a number of AI generated videos on remote sensing. They're all there, all about between 4 and 5 minutes. I think they came out quite okay. I would like to have your views on your comments on these videos, whether it's worthwhile doing more of them or, well, it's basically enough just as a demo. And then, as I said, we did a couple of videos on some of the requests, some of the comments that I've received where people have asked for specific things, and I thought, let's do them as well, let's include them. But if we remember, we are continuing, or we are busy with land surface temperatures, and specifically using land surface temperatures to generate urban heat hotspots or heat maps, meaning to identify urban areas. Remember, we used, well, this is now many, many months ago, we we looked at the various indexes using Landsat and Sentinel images to isolate or to identify and isolate urban areas or build-up areas. And we ran into this problem with bare soils, if you can vaguely remember correct. Anyway, so one of the methods that I found that people have used to identify and isolate urban areas or build up settlements was the idea of urban heat maps, meaning that the heat, the land surface temperatures in urban areas are much higher than in neighboring non-urban areas. So that's the basic idea behind it. So you want to identify these areas with above average, let's call it above average temperatures, land surface temperatures. Those are mostly urban areas, or could be classified as urban areas. So that's what we're busy with, and that's where we stopped in 157 before we took this little bit of a detour. And that's again the nice thing about doing this remote sensing journey is that we can just stop, we can start, we can take detours. It's really flexible. As people comment, new ideas come to light, we run with that, and then we go back to where we left off. Okay, so just please, boys and girls, we're standing at 490 subscribers. Let's get that to 500, please. Let's see if we can get it before the end of the week. Let's get that number up to 500 at least. Then I'm 50% towards the 1,000, and that's really the magic number, is that 1,000. When I started, 6 months ago, 7 months ago, I didn't even think I'm going to have 10 subscribers. So having 500 would be the world to me. So please, let's get that number up. Let's support the channel. Let's grow this channel together. Okay, so that's my little commercial. Done, dusted. Okay, so let's continue where we left off with urban heat maps, land surface temperatures. So just to confirm again, if you have a look at that 157, we worked basically to generate these time series charts and these images. So basically what we've done here, let me just go up again, is to say, okay, for my region of interest, and again, if you go back into these videos, you'll see that we've decided to use Cape Town, city of Cape Town municipal area, as our region of interest, because the one that I normally use, which is the municipality that I stay in, the urban areas is just too small and it's too sparse and it's too vegetation to get any. There's no much difference in land surface temperatures between the build-up areas and the non-build-up areas. So it doesn't work again. So again, that's a problem area that we have to address. But nonetheless, let's go on. And so we decided to go to Cape Town because Cape Town has a mass urban structure and a sizable non-urban area as well. So seems like a good guinea pig or good place to try this method. Okay, so We've loaded the city of Cape Town, normal stuff. We add the layer, we center it, we generate our clipping tool, and then I've added some time periods because I want to visually have a look at it. Those are the time periods that we've created. You'll see I've kept it constant in the same months, and I've chosen the 5th month to the 10th month, meaning I've selected winter. Now, the reason why I've done it is, again, similar to the other reasons, is the issue of bare soils. I want to diminish or I want to decrease the influence of bare soils. Now, the city of Cape Town doesn't have a lot of bare soils, but it does have. So, why I use winters, I want to decrease the influence of bare soils. Because in the summer, bare soils will be as hot, if not hotter than urban areas. And given the climatic and environment of the Western Cape, you will have much more bare soil in the summer than in the winter. Winter is much more vegetation, it's greener, etc. So it made sense to rather look at it from a winter perspective than a summer perspective. But again, that is up to your discretion. You can use your own discretion. You can use different months, different seasons, see what happens. In my case, we've used winter. Okay, so that's the first thing. So I'm going to generate 4 images for my region of interest, and I want to compare these images over time to see whether the land surface temperatures have increased or haven't increased. So this is not creating hotspots at yet, urban hotspots or heat maps as yet. It's just to generate the baseline data, to generate the baseline information. Okay, so that's basically what this script is all about, and that's pretty much presented in 157. Okay, so that's pretty much presented in 157 to create this map. So that is land surface temperature. I think that is a mean temperature. You'll see it's fairly stable. You can see the seasonal patterns in it, etc., etc. We've created a yearly map where we just generate an average land surface temperature for 2014, 2018, 2020, 2023. Remember, these are the dates that we've presented there, and you can see there's definitely an increase in average land surface temperatures for my region of interest. So this is not for urban versus non-urban areas, okay? This is purely for the area as a whole, but you can see that land surface temperatures have increased. Okay, 2013, there's a significant decrease. You can again see that 2013. So 2013 is definitely for a cooler period than years before that. You can see there was in 2018 a bit of a cool. Anyway, so that just gives you a background into land surface trends within the city of Cape Town in terms of our region of interest. And then we just generated the maps for each of these 4 periods. Okay, we've calculated a median image, a mean image, a maximum image. That's up for 2014, and so forth, and so forth, and so forth. Then we created the temporal difference, and that is our temporal difference image. Which would be, if we can go to our images, we'll find out what the color schemes. I would assume that yellow, red is an increase in land surface temperatures, and green, dark green, and most probably dark blue would be a decrease in land surface temperatures, where light blue would be sort of not much. Let's have a look. Yep, it's the temperature -3. You'll get blue, okay, and green. Okay, so up to that is still, I think, negative, and yellow, orange, red is increases. So you can see that. Remember, that's now 4. Let's have a look. What period is that now? That's from our temporal difference one. Temporal difference is the latter period and the early period. Okay, so that is 2013 subtracted by 2014. And if you just go there, you can see that most areas will be on the negative side because 2013 is less than 2014. Hence, only very few areas that experience an increase in land surface temperatures, where most of the locations experience a decrease, and that's just evident there. if we would change it to 2020, where is it now? If we change the latter period to, let's say, to uh, the earlier period, um, that one there, if we change that to 2020, then most probably the charts would look very, very different. Okay, so remember also in this code we built in the loops and all of these things so that we don't have to rerun them all over the time. So if you go back there, it automatically will select this as your latter period and this is your early period. Um, so we can just change the dates here or just delete that, for example, do this, and then we can rerun it. Okay, so it's not going to do that, so that's not going to work because it's looking for that period there. We most probably will have to delete it. Yeah, we'll have to do this, and then take that away. Let's see if we run it now. Cannot read it because it says 3. Okay, so yeah. So we'll have to change it. Let's do that. Yeah, so we'll have to manipulate these ones a little bit. We can put in we can change that to 2020, just duplicate it, and then it should run. So if we duplicate that to 2020 and 2020, and we run it, we'll see if we leave that temporal differ, you'll see, should see much more red. You see much more red. Why? You can see there, it now recognizes 2023 as a latter period, and which is much higher than 2014. Okay, so we can manipulate the code a little bit to create different maps and stuff. And it's interesting that these natural areas experience the highest increase in temperatures, which is interesting. These is natural areas here. Or we'll have to go and have a look and see what is these underlying periods here. Let's go satellite. Let's go and have a look and see. So that's that period there, or that area there, sand. You see this problem with sand. So that's definitely sand. You can see that. That's definitely sandy area here. And if we go, where's my other? That's also sand area there. Coming back to my argument of using the winter. So let's have a look here. There was a very hot period here as well. You can see that. That's also sandy area. Okay. Nonetheless, let's go back to it was, and you'll see there now it's going to be the latter period will be 2023, early period. So therefore, most of the area would have experienced a decrease in land surface temperature simply, and that's evident here as well. So that's pretty much what we've done in this particular script. We've generated a time series, and I think it's average. I like using median, but now and again I use average. Okay, that's just basically to generate it in Celsius. So that's the multiply, that's the scaling that needs to be done. I just want to quickly have a look and see. Yeah, mean. Okay, so it is mean. Calculate the monthly mean. Yeah, so it's mean. Okay, so that's the mean. So this is the mean. Okay, and so this would also be mean values, not the median values. And obviously we can change it there to median. We can change it there, median. Let's quickly run it now. Let's try to make a mental note of this, although I don't think it's going to change that much, but who knows? Let's have a look and see. So I'm going to take these ones. It looks very much similar. Oops, look at that. That looks very different for 23. Huh? So there's definitely a big difference here from 2022 to 2023. That's a huge difference. Almost doesn't make sense to a large degree. 20 degrees. Okay, but it's the scaling is anyway 2021, so that's just because of the scaling. So let's go back. Let's change it back to mean. So we can play around with the code to generate. Remember, the scaling factor is very important. Remember what I said? The scaling factor determines the values. Ne? So always make sure that your scaling factor talks to what is in the data set itself, the scales of the data set. To determine the scale of the data set, we go Google and we go data set, and we basically just search for that. And within the data set, let's go click on it. It will tell you the scaling factor, the resolution, which is 1,000 meters. So that's why we use 1,000 there. So always make sure, because again, let's see that is now 21.158. Okay, so remember that in 21.15, 21.46, 22.2. So let's make that 100. Let's make it 10, just to go extreme. Now have a look what the numbers would be. Okay, so let's have a look and see what the numbers will be. Remember, it was 21.4, 22.22, I think was the last one. So obviously it's now struggling a little bit. You see the numbers is now different. See, that was, if you vaguely remember, 2014 was 21 point, was it 21 point something? I can't remember. And 22 was 22 something something. So you can see the numbers have definitely changed, not dramatically, but the numbers have indeed changed. So always make sure that your scaling factor here is correspond to the scaling factor in the data set itself, in the catalog. Okay, so always make sure, try to get it as close as possible so that the numbers are accurate. Otherwise, yeah, as I said, the numbers are not going to be. The trend trends will most probably be the same, but the values most probably will be quite different, and it could be significantly different. So bear that in mind. Okay, so without repeating myself so many times, yeah, we've generated time series, land surface temperature time series for my region of interest average. We've created a yearly average chart for land surface temperatures for my region of interest, and then we've generated 3 images for each year for my region of interest, and we created the temporal difference between the early and the latter period. And that is so this is just presenting, displaying various images, data relating to land surface temperatures within my region of interest. Okay, so that is what this script is all about. Now, once we've got our bases, our foundations, we understand the concepts, we understand what we want to do, now it is time to actually convert this into urban heat maps or urban hotspot or whatever you want to call it. And that's typically what we're going to do in this particular piece of code. You'll see again, we are working with the MODIS dataset. There's MODIS, and we're creating a median and a mean land surface temperature. Now, I'm only created for the period 2023. Okay, so again, you can do it for all those periods. So you'll just build in, you either repeat it for each year, or you build a looping function to create it similar to what we've done here, where we created a looping function to generate the 4 images, the images for the 4 periods. Here I've only confined it to one specific period. Okay, because I just wanted to first see if this thing works. Okay, so as per normal, we start with our region of interest, we load it, we generate our map, region of interest, we center it around, and I'm not using a clipping tool per se, I'm just declaring my region of interest. I'm just declaring. I found that to work very similar to the map, the clipping tool. It's up to you. You can decide which one you want to use. It's up to your discretion. I found that declaring it works as good as the clipping tool. So let's use that specific one for the change. Okay. If you find that it says that it's not a function, it's not a valid function, you just create your clipping tool. Okay, so that's standard stuff. Then it's our declared period of time. So we have a start period and an end period. And you'll see again, I'm using my winter period. Okay, the winter time period. So again, that's up to you. That's your discretion. Feel free to change it up, change the dates, change it, see what happens. Just remember to include sufficient months within the analysis. You'll find that sometimes um, the images are not that reliable for a very short period of time. So keep the period fairly liberal, make it a little bit bigger, just to make sure you have sufficient valid images to do the analysis. As I said, if you define your period too small, meaning not a lot of room, then you may limit yourself to one image, which might not be a very good image. So rather 3 or 4 images and work with the average. I think that's much more reliable. Okay, there's my clipping function. So I did invoke a clipping function, and there's my normal modus data set. Okay, so just have a look and see. This is our modus data set. Aqua, land, surface, temperature, emissability data set. It's 8 days, so more than enough images per month. There's our time period, so it's actually up to the 7th. It's 1,000 meters. There's my band. And remember, my band has a scaling factor. Okay, so please take note. And it's in Kelvin. So we need to first scale it by 0.02, all the values, and then convert it from Kelvin into Celsius. Now, again, you don't have to do that. That's totally up to you. But just remember, when you do the interpretation, you have to interpret it within that context. You can't now say it's Celsius or it's actual values, because it's not, because you haven't scaled it. So please remember to take that always into account when you look at. So, this information sheet, this landing page of each of these data sets are so important, because it contains all this information, which are very, very important. Okay, so we've got the modus, and it's an image collection. Remember, we already have a start and an end, so we're not going to filter date by. We can just add that in here. Okay, but because we want to change it there and it runs automatically, let's leave it as is, because we may have multiple start periods and end periods. So let's leave it as is. Our filter bounds is our ROI now. This I actually add in. It very seldom works, but let's keep it in. And I've because I don't have any faith in this part, I have my clipping tool. But I can also have just clip.ROI in here. So I could also have dot clip and what did we say? It's ROI1. So I can also do that. Okay, it's the same as that. So now I've got 3 that's doing exactly the same. So I can delete that one. I can also basically delete that one. Let's keep it in. That's standard. You'll see, but it doesn't really work in many cases. So map clip tool, and then I've got my scaling here. This is where my scaling happens. So this is again standard, bringing in your image or your data set, clip it, and time it. Okay, here I bring in my scaling, where I take my image. There's my band. Take my band and I multiply it by 0.02. Why? Because that's the offset of the scale in the data set itself. You'll see that you multiply it by that. And then, as I said, we just subtract 273. Now that's the standard to convert from Kelvin to Celsius. You subtract by 273. And then I just rename it the band. Rather than have this long name for the band, I just make it LST. So that's pretty much what we do there. Nothing out of the ordinary stuff that we've done. So now I have my data set. I've set up my data set. I've clipped it, give it a time period. I have corrected the format of it, etc., etc. So now I sit with image because remember now I have a single image. Oh, sorry, I still have image collection. I still have to say whether the reducer, because remember there's going to be multiple images in this, so that's why it's image collection. So now I still have a whole lot of images, 13, 14, 15, 20, I don't know exactly how much, but we have a whole lot of images, but at least the images are within the defined period. They are clipped and they are reformulated. And I'm giving it a different name. Okay, so that's done. And here we go further, and here we're actually going to take the data set and we're going to create a median. Okay, so that's the important part there. So I could have actually just added in here to say dot median, and I can leave it like that. And it will have taken the median there. So that's also a possibility, but we've included it here. So that is just to make sure it's clipped. So I could actually just delete those two and I'll just leave it there. So that's also possible here. But we've decided to do it there simply because otherwise it would rectify it for the whole world, and that maybe just becomes much more tedious to do from a time period and a what do you call it when you use RAM period, whatever. But yeah. So I've already clipped it, so it's much smaller, so that was much quicker. It uses much less whatever they use here. Okay, so it's just quicker. And I've used the median, and there's my visualization, and there I visualize it. And it is modus list, so there it is. And you'll see this is the same as what we've done here. So if you go there, and that's for 2023, né? So that would be something that looks like that. You'll see the two is very similar. Okay, the difference just basically is the time frames. And it's mine, in my case, it's a median. In this case, remember we used a mean. So that's a difference, but essentially it's exactly the same thing. It's exactly the same thing. Now here's our Landsat image, our land surface temperature image. Sorry, I don't know why I keep on saying Landsat. So there's our Landsat. So this is our baseline image. This is our baseline image. Again, derives from here. Now what we want to do is we want to convert this into our urban heat map, into our urban hotspots. And this is what we've done here with these images. So ultimately, we're going to get something that looks like that. There's our urban heat map. That's our, in the red, that's our urban heat map. So this is basically, according to this method, this is the urban area of the city of Cape Town. Because theoretically, it's urban, it's land surface signature, its signatures, heat signature, it's higher than the signature in the adjacent, the non-urban areas. So that's ultimately what we're interested. But our beginning point is our standard land surface temperature. This is the mean one, the mean one, and the median one. But these three are exactly what we've done here. Okay, so that's just the mean, median, and mean one, which is these ones here. Okay, you'll see there is the composite. The composite, which is the data set. Remember, there's our data set with the end and time, and we just have a median and a mean, and there must be we didn't do a sum. No. So that's just the three data sets, but you'll see this mean one in this medium one here, and this median one should be exactly the same data sets. And you'll see there, if I do this, you see it's exactly the same. So I'll just repeat myself. Okay. So up to there, it is just, and obviously there is the color scheme of it, and there's the map layer. So what we've done up to this point, up to here, is just to create these three images. Well, two of them are exactly the same, but we've created it. Temperature is between 17 and 28 degrees. Blue is cold, red is hot. Okay, so that's it. Now what we want to do is, now we need to start working on calculating our heat maps, our hotspots, urban heat maps or urban hotspots. And that's what we're going to do in our next video tutorial, is this part of the code where we're going to end up to identify this urban heat map. And I said the idea is to say, okay, this actually should be our urban areas because its land surface temperature here is much higher than the surrounding areas. That's what basically the theory or the argument is. And if we overlay this, you'll see it basically overlays exactly with these hot areas here. Remember, orange, green, there's some orange here. Okay, anyway, so that's what we're going to do in the next video, is to convert our Landsat. I keep on Landsat, man. Our land surface temperature image, we're going to convert into urban heat maps, urban hotspots, based on the argument that, as I said, urban areas attract, contains, keep heat much higher than surrounding areas. Okay, so let's park there for now, up to this point. Let's park there, and then we're going to continue in our next video. We're going to go to say, okay, now, where did we go now? Then we're going to say, okay, now, how do we isolate these areas, etc., etc. Okay, so let's park it for there. And yeah, thanks for joining me. Appreciate. And please, as I said in the beginning, go and like and subscribe, share, send me some comments. It makes the journey less lonely, and that helps a lot. Let's build it together. Let's explore together. Let's go boldly where nobody else has gone. And yeah, let's learn from one another. I appreciate your support. I appreciate all the kind words. And like and subscribe, share, and I'll see you on the other side.